Oh, hey there folks, welcome back for another video tutorial. In this particular video lecture, folks, I'll be talking about how to calculate a one-way ANOVA. How do you calculate a statistic that evaluates mean differences between two or more levels of an independent variable? All right, folks, so on page 367, I'm going to walk through number 10 since that resembles closely a problem that you'll be completing for your homework assignment. Sometimes when you're completing ANOVA problems, you'll just be given a summary table, and within that summary table, you'll be given information about between treatments, within treatments, and total scores. And these between treatment scores and within treatment scores will consist of sum of squares, degree of freedom, and mean square, which remember is very much like the variance. In fact, it is the variance. A variance is the average square distance that a score is away from the mean. Now within these problems, you'll be given some blanks that you'll need to figure out, and then other scores will just be given to you. In this particular example, the total score is given to you. 10 is listed as the mean squared score for between treatments. You have a blank for the within treatments mean square. And then finally, there will be an F ratio that you will eventually have to complete. So, the problem gives us a hint that we need to start calculating our degree of freedom first. And we should really heed that suggestion. Let me lay out some of these degree of freedom formulas. Degree of freedom total, that formula is capital N minus 1. Capital N, of course, stands for the total amount of individuals in your study, or the total amount of participants. We have degree of freedom within, which is capital N minus K, and we have degree of freedom between, which is K minus 1. Now, K is a new abbreviation you all are seeing. K simply means number of groups. So you'll want to keep that in mind as you're moving through these formulas. Now, the worded portion of this problem tells us that there are 10 participants in each condition, and there are 4 treatment conditions. 4 treatment conditions, 10 individuals per treatment condition. So it stands to reason that we got 4 treatment conditions and there's 10 per condition. Stands to reason that there are 40 individuals total in the study. So in other words, capitalize N is 40. Again, how did I get that? I got that because I looked at the number of individuals that were said to be in each condition and the amount of conditions, and I simply multiplied those numbers to get the total amount of individuals in the study. So in this particular case, capitalize N again is 40, and in order to get our degree of freedom total, we're going to take 1 from that. When we do so, we end up with 39. Now, what I would encourage you to do is, as you work your way through each set of formulas, begin to plug them into your ANOVA summary table. So degree of freedom total is 39, so we'll plug that in there. So still heeding the advice of the authors of this textbook, we are going to calculate our degrees of freedom. Moving on to within, we take 40 and we subtract 3 from it. No, excuse me, 4 from it. And when we do that, we end up with 36. So our degree of freedom for within is 36. and then we calculate our degree of freedom between. Degree of freedom between is 4 minus 1, and when we do that we end up with 3. So we will plug that into our ANOVA summary table there. Alright folks, so the goal is to eventually get to the F ratio, and you want to be careful to just answer what is being asked of you in the problem. Sometimes what's being asked of you is to determine significant difference across the groups. Sometimes they're just asking you to complete the ANOVA summary table. This is an example of the latter. They're just asking us to complete the ANOVA summary table. So moving from there, many of you may wonder, okay, where do I go next? Well, given that you have a mean square of 10 for between treatments, it stands to reason that you may want to go the route of figuring out the sum of squares, since you got two key pieces of information that can help you get that. The mean squares for between, let's look at that formula. The mean squares for between formula is the sum of squares between divided by the degree of freedom between. Now, in our particular case, given the answer that was provided to us in this example and the answer that we calculated, that being the degree of freedom between, we already have the mean squares between, which is 10. The sum of squares between is still a question mark, and we have degree of freedom between, which is 3. Now, if dividing the sum of squares between by the degree of freedom between gives us the mean square between, then it stands to reason that doing the opposite operation, so instead of dividing here but multiplying here, doing the opposite operation across these digits will give us what we need there. Okay, so in other words, in order to get our sum of squares between, we would have to multiply the degree of freedom between by the mean square between. When we do that, 10 times 3, we end up with our sum of squares between, which is 30. Okay, so let's go ahead and plug that into our ANOVA summary table. Now from there, folks, once you got the sum of squares between, many folks may want to tackle this, but I would say hold off on calculating your mean squares for within treatments, because you have two key pieces of information here that could lead you to get your within treatment sum of squares a lot faster and easier. Okay, so let's talk about some of these sum of squares between and within formulas. So the sum of squares between formula is SS total minus SS within and the sum of squares within formula is the sum of squares of all of the different treatment conditions. Now, to get between, you have to take away within from total, and we already got that, right? We got 30. We've already established that 174 is the total, but SS within remains a mystery, right? So if subtracting within from total gives you between, then it stands to reason that subtracting between from total will give you within, okay? And if we do that, if we take 30 from 174, our within treatment sum of squares is going to be 144. So, easy way to check yourself, folks, is just to make sure that all of your sum of squares and degree of freedom totals are the equivalent of adding up your between treatments and within treatments. In other words, adding these two columns should always give you that total column for sum of squares. Adding these two rows should always give you that total degree of freedom there. Sum of squares within, we don't have information on each sum of squares as it pertains to each treatment condition, so we had to go the route of simply taking between treatment sum of squares from the total to get the within treatment sum of squares. All right, from there, we need to calculate our mean squares within. Our mean squares within formula is sum of squares within divided by degree of freedom within. Sum of squares within, we've established is 144. When we divide that by 36, which is our degree of freedom within, we end up with 4. And that is our mean square within. And then finally, to calculate our F ratio, we divide mean square between by mean square within, which is 10 divided by 4, and this gives us 2.5. So our F ratio is 2.5 here. Now, I know some folks may be wondering, okay, why are we even calculating this statistic? So I get the math now that you've gone through it, but what's the whole point? The reason why we're calculating this statistic, folks, and let me just erase everything on my whiteboard here. The reason why we're calculating this statistic is because we're trying to avoid compound error, and compound error is a situation that may occur if you're evaluating more than 2 treatment groups and you're trying to use a t-test to do so. So folks, continue to take a look at the whiteboard. On this whiteboard, I place an example which will really highlight some of the compound errors that you run into if you try to employ a 2-sample t-test across more than 2 treatment conditions. In this example, we have one factor or one independent variable, and it has 4 different levels. All of these different levels deal with interventions that may be put into play if somebody was performing at a subpar level in the academy or maybe in primary school, secondary school, etc. So we got tutoring, ABC, mouse, scaffolding with peers, and reading. Under each of these column headers, we have numerics that represents grades. And it stands to reason that since we got 3 individuals per level of the independent variable, that we have 12 participants in the study total, simply taking forward, multiplying it by 3. Now, let's say we wanted to use a 2-sample t-test to assess significant differences across these groups. Here's what would happen. So as the researcher moved to assess a significant mean difference across tutoring and ABC mouse, they would have to take into consideration that 5% error rating, or that 5% alpha level. Remember that alpha level is really an indication of the likelihood that you are committing a type 1 error. Type 1 error is when you reject the null hypothesis when you should have accepted it. So remember, in research, nothing is ever fact. All you do is put forth hypotheses and you gather evidence for it, and that evidence is all probability based. So we have a 5% error rating that will occur once we assess the significant difference across tutoring and ABC mouse. 5% would show up across tutoring and scaffolding with peers, and then you would have 5% show up across tutoring and reading. Okay, moving on from comparing tutoring to the other levels of the independent variable. When we look at ABC mouse and scaffolding with peers, we got 5%. When we look at ABC mouse and just reading, we have 5%. And then finally, we got to deal with scaffolding with peers and reading, right? Just making that pair-wise difference, and we would end up with 5%. So by the time it's all said and done, by the time we ran two sample t-tests across all the likely pairs that may result from these levels of the independent variable, we're essentially dealing with, a 30% alpha level rating. In other words, there's a 30% likelihood that if we find a significant difference, that there is really not a significant difference. That's a big issue, okay? And that is why the one-way ANOVA has been put into play. So the previous example focused on a one-way ANOVA, folks, and a one-way ANOVA, again, just indicates one IV with varying levels, typically two or more, okay? But you can have a factorial ANOVA or something like a 2 by 4 by 5 ANOVA. That's an example of a factorial ANOVA. And this would be a three-way ANOVA. Okay, so it can get extremely complex. So what we're talking about in this course is just the foundation, just a simple one-way ANOVA, but it can get complex. You can have three independent variables with varying levels. So the way I've written it out here would indicate that you got one independent variable just by the sheer indication of the number with two different levels. Okay, this independent variable has four levels, and then this independent variable has five levels. Uh, so imagine all of the pairwise differences you would have to make across those different groupings, okay? And imagine the error rating that would result if you use the two sample t-test. Big problem, and that's why we shift gears and we go with a one-way ANOVA to remedy that problem. Now, what if the problem that we were working before this example required you to determine significant difference? How would you go about doing so? Let me clear my whiteboard again. So we ended up with an F score of 2.5. Right? And in order to determine significant difference, you would need to go to your F critical table. So you will find this at the end of your textbook. You can also find a plethora of F tables online. I'm just going to switch over to my internet web browser that already has an F critical value table up. And what you would do is come to this table and utilizing the probability or the alpha level that was given to you for the problem. Let's say it was 0.05. Okay. And utilizing your degree of freedom between and within, you would determine the F critical value that you would use to determine significant difference. Okay. The degree of freedom in the numerator, again, folks, is the degree of freedom between. Okay, and for the example that we were working, the degree of freedom between was 3 because we had four groups and we subtracted one from it and we ended up with 3. And our degree of freedom in the denominator or within, okay, is 36 because we took into consideration the entire group of individuals that we were working with, and which was 40, and we subtracted the groups from it, which gave us 36. Okay, so let's say our degree of freedom numerator again is 3, right? So we would go to that particular column header, right? And then we would go all the way down until it lined up with our degree of freedom in the denominator or our degree of freedom within 36. So let's scroll down a little bit. Okay, maybe a whole lot. So we're scrolling, we're scrolling, we're scrolling, and once you hit 30 degree of freedom in the denominator, we jump to 10-point increments. I would go in this case with 40, just round up. Okay, and here we are trying to determine our F critical value. So if 0.05 was given to us, we would go to that specific row that aligns with the right degree of freedom in the denominator, and we would come over until we found our F critical value for our study, which is a positive 2.84. So the F critical would be 2.84. Now remember folks, when we were talking about z-scores and critical region boundary markers, we went with plus and minus 1.96 a lot of times because we had an alpha level of 0.05. Folks, your F critical values are always going to be positive and your F ratios are always going to be positive. So you don't have to utilize a whole lot of cognitive flexibility in determining if you need to accept or reject the hypothesis. Essentially, folks, what you're going to do is compare what you calculate in step 3 of your hypothesis testing, which is the F ratio in this case, to step 2, which deals with locating the critical region. You're going to compare these numbers, and if what you calculated is higher than what you have for your F critical value, then you would reject the null hypothesis. Okay? So if this number is higher than this number, if the F ratio calculated is higher than the F critical, you reject the null hypothesis. If it's lower, you would accept. So if the example that we were working was actually asking us to determine significant differences across this group, if they just show up, because they're not giving us specific information about where the differences show up. In other words, it's not pinpointing specifically which pairs are different. It's just assessing if a difference occurs across the 4 groups. Okay. If this number was higher than 2.84, we would reject the null hypothesis. But since it is not, we will be accepting the null hypothesis as it relates to our example. Now, in order to determine where the significant difference lies, you will have to calculate post hoc tests. And these are additional hypothesis tests that are done after an ANOVA is determined to be significant so that you can determine exactly which mean differences are significant and which are not. Okay, so I think that's enough for this video, folks. I hope that it was extremely helpful. Feel free to leave me a comment, leave any suggestions, and contact with me with any video tutorial requests you have moving forward. Take care.